Okay, good evening everyone. I welcome you all to the problem solving session of the NPTEL course on thermodynamics. I am Pradeev E. I am one of the TA for this course. So this is week 6 problem solving session, and I have some, first I will solve some questions on the week 5 assignments, and then I have some questions on ideal gas mixtures and so on. So the first question, match the correct pairs. So here, can someone in the audience tell what is the right answer here? You can either put in the chat box or you can unmute and answer. So Boyle's law is option 3. Yes, so that is right. Boyle's law states PV equal to constant at when temperature is constant. Then Charles' law that V by T is equal to constant at constant pressure, and then Gay-Lussac law states P by T is equal to constant at constant volume. Second question, the perfect gas Cp and Cv are constant, function of temperature only, function of temperature and pressure. So the answer is constant. So, and in the next question we have semi-perfect gas or an ideal gas, Cp and Cv are function of temperature only. So this is true. So for perfect gas, Cp is equal to constant and Cv is equal to constant. For ideal gas or imperfect or semi-perfect gas, so for both of them, Cp is just a function of temperature alone. So it is not a, it need not be a linear function, but it could be a polynomial or some other function, but it is only a function of temperature. And that is G of T. Whereas for real gas, Cp is a function of temperature and pressure. Similarly, Cv is a function of temperature and pressure. Now the fourth question, the graph of a specific enthalpy and internal energy versus temperature for an ideal gas must be straight lines. So this is false because it is a function of temperature, but it can be any function, it need not be a linear function. Next question, ideal gas. An ideal gas is contained in a container which occupies a volume of 100 centimeter cube at 25 degrees Celsius at 1 atmosphere. The number of molecules of gas in the container are we have some options. So now this can be solved using the Avogadro law. We know for Avogadro law, 1 mole of 1 mole of gas contains 6.022 into 10 power 23 atoms or molecules. So they have given it as a molecule. So now this is also 22. This occupies 22.4 liters of volume at 1 atmosphere and 0 degrees Celsius. Now the temperature is different and also the volume is given. So using this we can back calculate the number of molecules. So we know for 22.4 liters, it is 6.022 into 10 power 23 molecules, and so this is at 0 degree Celsius, or I will write it as 298 Kelvin. Now for 1 liter, or 1 liter is equal to 1000 cc, this is 6.022 divided by 22.4 into 10 power 23, and if it is now if you want for 100 cc, it is 6.022 into 10 power 23 by 22.4 into 10. So this is at 298 Kelvin. Using the ideal gas law, like PV equal to RT, if only the temperature is changing, we can say volume is proportional to temperature. Now based on this, for 100 cc at 290, so we want it at 25 degrees Celsius, so that is, so this is 273 Kelvin and this is 298 Kelvin. So at 298 Kelvin, volume, the number of moles is 6.022 into 10 power 23 by 22.4 into 10 into 273 by 298. So can you solve this? Paul, did you get the answer?
No, I'm still calculating, sorry.
.46 into 10 power 21. Yeah, that is right. So that is option 3. Now, which of the following is the correct statement for Dalton's law of pressure? The pressure of gas mixture is equal to the sum of pressures each gas would exert if it is existed alone at the mixture temperature and volume, or at any temperature and volume, or at the mixture temperature and any arbitrary volume, or none of the above. Can you tell me which is the right option? So this is option A. The gas mixture with exert a volume, exert a pressure that is sum of the pressure that it would have exerted when it existed alone at the mixture temperature and volume. Okay. Now, which of the following is correct relationship between mass fraction Y and mole fraction X for a species I, for ith species? Mi represents the molecular weight of the ith species and n represents the total number of species. Now we know molecular weight Mi is expressed in terms of gram per mole. And we have mass fraction and mole fraction, right? So, assume we have gases A and B, and we want to calculate the mass of the gas A in the mixture AB. So now how do we write using molecular weight? So molecular MA gives the weight of gas A for 1 mole, and similarly MB says weight of gas or the species B for 1 mole. Now if I multiply with the mole fraction xi, so xi says number of moles of A for 1 mole of mixture. Okay, so now we have 1 mole of mixture, and now we can we know there will be xa moles of gas A or the species A in this 1 mole of mixture, and similarly xb for moles of B in the same 1 mole of mixture. Now if you want to calculate the mass of the gas A in this 1 mole of mixture, then what do? We will multiply xa plus into MA. So this is moles, and this is in gram per mole, and mole get cancelled, and then finally we will have grams. So xa into MA is the mass of A in that 1 mole of mixture, and similarly xb into MB is the mass of species B in 1 mole of the total mixture. So if you sum all this, we will get the mass of the total mass of the mixture. So this expression, adding these two, we will get mass of 1 mole of mixture, right? And similarly xa MA, this term will alone give me mass of A in 1 mole of mixture. So what if I have XAMA divided by XAMA plus XBMB? Now this is mass ratio or YB, because I have MA by total mass, MA plus MB. So from this you can say the right answer is option E. Now, which of the following is correct expression for gamma? So you will find all of them are right, because yi is mass ratio, mass fraction, and Cpi is specific heat on mass basis. So if you want to calculate the Cp for mixture, we would sum up the product of Ya and Cpi. So this will be the Cp of mixture. So gamma of mixture will be Cp mix by Cv mix. So this can be obtained using the summation of YICPI YICVI. And similarly this can also be expressed on molar basis, and that is in the second option, and both these are same, so the third expression sum was both these are. So determine the next question is determine the specific volume of superheated vapor at 40 megapascal and 780 degrees Celsius using ideal gas equation and generalized compressibility chart. So now the 780 degrees Celsius is can calculate 1053 Kelvin. Using ideal gas equation, we know PV equal to RT. We want to find the specific volume, so you know it is PV equal to mRT. So P specific into specific volume becomes RT. Now we want to calculate V is equal to RT by pressure. So R we know R for, so this is for the vapor, water vapor, so R for H2O is R bar by molecular weight of H2O, and that is 8314 divided by molecular weight of H2O is 16 plus 2, that is 18. So now we have 8314 by 18 into temperature is 1053 and pressure is 40 megapascal, so in SI units we have 40 into 10 power 6. So can you calculate the specific volume? Yeah, 0.012 meter cube per kg. And now using the compressibility chart we can find. So for that we need to calculate the reduced pressure and reduced temperature. So reduced pressure is given by the actual pressure by critical pressure, and actual pressure is 40 megapascal divided by critical pressure is 22.06. So we can calculate the reduced pressure. And similarly for temperature, reduced temperature, it is actual temperature by critical temperature, and that is 1053 divided by 647.1. So can you calculate this? 1.627. Now from compressibility chart we will be having some chart like this. Here you can see Z is PV by RT. So Z equal to PV by RT. So now we have these two values. Using this in the compressibility chart we can calculate the value of Z. So we have reduced pressure of 1.8 and temperature 1.6. So for 1.8 reduced pressure we will have a line here, and for 1.6 reduced temperature we'll have somewhere here, right? This is 1.5 and 1.6 could be somewhere here. So we can take a value of 0.88. So we write it as 0.88. Now volume equal to 0.88 into R is 8314 by 18 into temperature is 1053 divided by pressure, that is 40 into 10 power 6. Can you calculate this? 0.01. So this is again meter cube per kg. So now if you find the difference between these two, delta, this we can write it as compressibility or V prime, and this is V. So V minus V prime is 0.012 minus 0.011, so that is 0.001 meter cube per kg. So we have to find the difference in magnitude. So that is what we have. Do you have any questions? So in the next problem, we have a gas mixture of the following composition. So the composition is given on mass basis. First we have methane of 58%, carbon monoxide of 14%, hydrogen of 18%, and hydrogen of 10%. The molar constant pressure specific heat values are given. The gaseous mixture undergoes a polytropic process from state 1 of 1 bar 298 Kelvin to state 2 of 3 bar 400 Kelvin. Assuming that the specific heat values are constant, find the work transfer per kg of the mixture and heat transfer per kg of the mixture. So now we have P1 as 1 bar, P2 as 3 bar, T1 is 298 Kelvin, T2 is 400 Kelvin. Since they have mentioned that it is a polytropic process, we know PV power n is equal to constant. Here to calculate the value of n, we don't have the volume values, but we have only the temperature ratios. So we know T2 by T1 is equal to P2 by P1 power n minus 1 by n. So this we would have derived earlier. Using this, we can substitute the known values and get the value of n. So you know this is T1, T2 is 400 by 298 equal to P2 is 3, P1 is 1, the whole power n minus 1 by n. If you take log on both sides, you will have log of 4 by 3 and approximating 298 to 3, then we have n minus 1 by n into log of 3. So now we have n log of 4 by 3 equal to n minus 1 log of 3. Can you calculate the value of log of 4 by 3? So generally in this case we will take natural logarithm, so it should be log base e, so it is ln. I think even though both will give the same answer, so we will go with this law. So this is 0.125 into n equal to similarly log of 3. This is 0.477 into n minus 1. Now we have to solve for n. No, take it simple. So we have 0.477 n minus 0.477. So we take on one side, we will have n into 0.477 minus 0.125 outside plus 0.25 minus 0.477 is equal to minus 0.477. So n is 0.4772. Calculate this. Yes, 1.35. So this is the value of n. Now we know W work transfer is V1 minus P2 V2 by n minus 1. So this can be written as R of T1 minus T2 divided by n minus 1. So now we want to know the value of R. So here the R is R of the mixture. That is R mix is equal to R universal gas constant divided by molecular weight of the mixture. We have to calculate the molecular weight of the mixture to proceed further. We know molecular weight is in gram per mole. So if you want to find the molecular weight of the mixture, then we can have a summation of xi mi if xi is molar fraction, but we are given only the mass fraction. So for mass fraction we will have 1 by mx is equal to summation over yi by mi. So how do we get this? This is in gram per mole. If you assume that we have a unit some another, so 1 by m is mole per gram, and now you have the mass fraction. So in 1 kg of the mixture, you can start calculating how many moles of each fraction will be there, and you can sum it up to get the total moles of the mixture. So in 1 kg of mixture we will have yi or ya kg of A, and similarly yb kilograms of B. Now if you multiply this with 1 by m, you will get, you multiply ya into 1 by mA. This will give you moles of A in 1 kg of mixture. Similarly, yb into 1 by mb will give moles of B in 1 kg of mixture. Now if you add these two, you will get the moles of A plus B in 1 kg of mixture. So that is again mole per kg. Now if we take a inverse, we will get gram per mole of the mixture. So that is how we got this. Now 1 by mix is what we have to calculate, and further on the right hand side we have the 0.58 divided by, or I will write first, y of CH4 divided by molecular weight of CH4 plus y of CO by molecular weight of CO plus y of hydrogen by molecular weight of hydrogen plus y of nitrogen by molecular weight of nitrogen. So this is 0.58 divided by molecular weight of methane is 12 plus 4, that is 16, plus y of, that is mass fraction of carbon monoxide is 14%, so that is 0.14 by molecular weight of carbon monoxide is for carbon monoxide we have 12 plus 16, so that is 28. So 28 here, plus for hydrogen we have 18%, that is 0.18 by 2, plus nitrogen we have 10%, 0.1 divided by this is molecular weight of nitrogen is 12. If you add all this and then calculate, take the reciprocal, we will calculate the molecular weight of the mixture. So that is 7.42 gram per mole. Now we can calculate the R, which is 8314 R of mixture, 8314 by 7.42. That is 1120.5 joule per kilogram Kelvin. Now work transfer is, we had here R into T1 minus T2 divided by n minus 1, so that is 1120.5 into T1 minus T2 is 298 minus 400 divided by n minus 1 is 0.355. So we can calculate the work transfer. That is, this is minus 312.46 joule per kg, or minus 312.9 joule per kg. We have calculated the work transfer. Now we have to calculate the heat transfer of the mixture. So we know del Q is, sorry, Q Q is del U plus W. We know the value of W. We need to find del U. Del U is also given by Cv into temperature. So now for this we need to calculate the Cv of the mixture. So to calculate the Cv of the mixture, we can have Cp of the mixture minus R of the mixture. So for Cp of mixture, we can have summation of mass fraction into Cpi divided by molecular weight of I. So this is for the methane we have 0.58 into Cp is 35.06 divided by molecular weight of methane is 16. Now for carbon monoxide we have 14% and 28.8. For carbon monoxide molecular weight is 28. Similarly for hydrogen we have 18%. And molar constant pressure specific heat is 29.01. Similarly for the last component nitrogen, it is 10%, and molar constant pressure specific heat is 28.87. So this is 4.129 kilojoule per kg Kelvin. So now we can calculate Cv of the mixture, that is Cp minus R. This is 4129 minus 1120. So Cv is 3009. Now delta U is Cv into delta T, so that is 3009 into final temperature is 400 Kelvin minus initial is 298 Kelvin. This is 306918 joule per kg or 306.9 kilojoule per kg. Q is equal to delta U is 306.9 plus work transfer is, we had a negative value of 312.9. So total we have minus 6 kilojoule per kg. This is roughly 6000 joules per kg. Next problem, a rigid tank that contains 1 kg of nitrogen at 25 degrees Celsius and 300 kilopascal is connected to another rigid tank that contains 3 kg of oxygen at 25 degrees Celsius and 500 kilopascal. The valve connecting the two tanks is opened and the two gases are allowed to mix. If the final mixture temperature is 25 degrees Celsius, determine the volume of each tank and final mixture pressure. So now for the first nitrogen, we have PV because both the initial temperature are same. I'm taking it as T. Now V1 can be calculated using this expression. So for M it is 1 kg, M1 is 1 kg, R1 is 8314 by 28 into temperature is 25 degrees Celsius. So 25 degrees Celsius is 298 Kelvin. And P1 is 300 kilopascal, that is 300 into 10 power 3. So we can calculate the value of V1. So this is 0.295 meter cube. Similarly, P2 E2 is equal to M2R2T. So V2 is M2 3 kg into R2 of 8314 by 32 into temperature T is again 298 Kelvin and P2 is 500 kilopascal. So that is 500 into 10 power 3. Can calculate the volume of V2. So this is 0.464 meter cube. After mixing, the final temperature is given. Final temperature of the mixture is given as 25 degrees Celsius. So you know P mix, V mix equal to R into T mix, or actually this M mix R into T mix. We have to calculate the value of odd mix. So that is R mix equal to R bar by molecular weight of the mixture. molecular 1 by molecular weight of the mixture is summation of yi by molecular weight of the individual species. So yi for y nitrogen is 1 by 1 plus 3 kg, so that is 0.25, and similarly y for oxygen is 3 by 1 plus 3, that is 0.75. Now we have 0.25 divided by molecular weight of nitrogen is 28 plus 0.75 by molecular weight of oxygen is 32. And if we take the reciprocal, we get the value of molecular weight of the mixture. So this is 30.9 gram per mole. Now if we substitute in this equation, P mix is what we have to calculate. So P mix equal to mass of the mixture is totally 4 kg. We have 1 kg of nitrogen and 3 kg of oxygen, so that is 4 into R is 30, characteristic the universal gas constant by molecular weight, so that is 8314 divided by 30.9 into temperature of the mixture is given as 25 degrees Celsius, that is 298 Kelvin, divided by the volume of the mixture. So volume is the summation of the previous of the individual chamber volumes, that is 0.295 plus 0.464. Using this, the pressure of the mixture can be calculated. So this is 422,557.7 pascals, that is 422.5 kilopascal. The next problem, mixture that is 15% carbon dioxide, 5% carbon monoxide, 10% oxygen, 70% nitrogen by volume undergoes adiabatic compression process having a compression ratio of 8:1. If the initial state of the mixture is 300 Kelvin and 100 kilopascal, determine the makeup of the mixture on the mass basis and internal energy change per unit mass of mixture. So when you compress it adiabatically, we will not know the value of gamma. So during adiabatic compression, we know PV power gamma is equal to constant, but here it is a gamma of the mixture, so that is Cp of the mixture divided by Cv of the mixture. So to calculate the Cp of the mixture, it is summation of mass fraction into, or you can have volume fraction into Cp I thought. So this is again molar basis. Cp on molar basis is represented as Cp bar. To calculate the Cp bar, we know that for monatomic gases, gamma is 1.667, and for diatomic gases, gamma is 1.4. For triatomic gases, gamma is 1.33. Now carbon dioxide is a triatomic gas. Carbon monoxide, oxygen and nitrogen all are diatomic gases. Using this gamma and molecular weight of the individual constituents, we will be able to calculate the Cp of the individual constituent. So this will be again here Cp bar. So we can calculate for carbon dioxide. Gamma of CO2 is 1.333. That is Cp bar of carbon dioxide by Cv of carbon dioxide is 1.333. And we know Cp bar minus CO2 minus Cv bar of CO2 is equal to R, that is 8314. So from this expression we know Cp of CO2 is substituting that here, so we can have a general expression that is gamma of Cv CO2 minus Cv CO2 is equal to R dot. So that will be gamma minus 1. So Cv CO2 is R bar by gamma minus 1. Gamma CO2 minus 1. So Cv bar of CO2 is 8314 or 8.314 by 1.33 minus 1. This is 25.194 kilojoule per kilomole Kelvin. Similarly, Cv bar of the next gas is CO equal to 8.314 by gamma of CO, so that is 1.4 minus 1. that is 20.785 kilojoule per kilomole Kelvin. So now for all the diatomic gases this will be the same, that is for Cv of nitrogen and Cv of oxygen. Now Cv of mixture is summation of xi Cvi bar, so that is 15% of carbon dioxide is 0.15 into 25.194 plus all other diatomic gases we can take it as a 1 unit, so that will be 0.85 because this is 0.15, the summation has to be 0.85, yes, into Cv of the diatomic gases, that is 20.785. This is 21.44 kilojoule per kilomole Kelvin. Now we want to calculate our mixture to calculate the Cp. This is universal gas constant by molecular weight of the mixture. So for the molecular weight of the mixture, it is summation of xi into molecular weight of the individual species. So that is x of CO2 into molecular weight of CO2 plus x of carbon monoxide, molecular weight of carbon monoxide, plus x of nitrogen plus into molecular weight of nitrogen plus x of oxygen into molecular weight of oxygen. So this is 0.15 plus carbon monoxide is 5% plus 10% of nitrogen, plus 10% of oxygen and 70% of nitrogen. And here molecular weight of carbon dioxide is 12 plus, so it is 44, and molecular weight of carbon monoxide is 12 plus 16 is 28. For nitrogen it is again 28, and for oxygen it is 32. This is 30.8. So out of now we need to calculate Cp of mixture is Cv of mixture minus R plus R, so that is 21.44 plus 8.314. This is 29.754. Now gamma is 29.754 divided by 21.4. This is 1.388. Now we have got the gamma of the mixture. So gamma of mixture is 1.388, P1 and T1 is given 100 kilopascal and 300 Kelvin. 100 kilopascal, 300 Kelvin. So V2 by V1 or the compression ratio is also given as 8:1. Now we can calculate the P2 and T2. P2, we know PV power N is equal to, or gamma is equal to constant. So that is P1 V1 power gamma equal to P2 V2 power gamma. P2 is P1 V1 by V2 power gamma. So P2 is P1 is 100 kilopascal, or we write it as kilopascal, and V1 is 8 power gamma is we just calculate a gamma, that is 1.388 for the mixture. So this is 1792.6 kilopascal. Similarly, the temperature expression, we have T2 by T1 is equal to V1 by V2 power gamma minus 1. So that is 8 power, so T2 is T1 into the other term, so we have 300 into 8 power gamma minus 1 is 0.388. So that is 672 Kelvin. So now we have to calculate the mass basis at this high pressure and temperature. So for mass basis, from the calculation of the R, from the calculation of R of the mixture itself, or molecular weight itself, we can calculate. Now we need to we can find the internal energy. So internal energy change is C initial T2 minus T1 So So CV mixture on mass basis is CV mixture on molar basis divided by into molecular weight of the mixture. CV is divided by. So for the CV bar we had kilojoule per kilomole Kelvin, and molecular weight we have kilojoule per kilogram Kelvin. Sorry, this is for the CV on mass basis, and molecular weight we have kilogram per kilogram. So if you divide this by this, we will get this, and this is 30.8. So CV of the mixture on mass basis can be calculated. That is 0.696 kilojoule per kg Kelvin. Now delta U is equal to 0.696 into, do we have the total mass? We don't have the total mass, so we can calculate per kg. T2 is 672 minus T1 is 300 kg. That is 258.9 kilojoules per kg. Similarly, to find the mass fraction, we have earlier seen in one of the from here, mass fraction is given by this expression. Molar fraction into molecular weight of the individual species divided by summation of all the terms. So VI is XI divided by summation of XI. So we can calculate the molar fraction of carbon dioxide. Y of CO2 is X of CO2 by molecular weight of CO2 divided by the total fraction CO2 and CO2 plus X O2 M2 plus X nitrogen M nitrogen. So X CO2 into M CO2 is 0.15 into molecular weight of CO2 is 44. That is 6.6. XCO into molecular weight of CO is XCO is 0.05 into molecular weight of CO is 28. 1.4. Then XO2 into molecular weight of O2 is For oxygen, the percentage is 10% into 32, so this is 3.2. X nitrogen into molecular weight of nitrogen is 0.7 into 28. So this is 19.6. If you add all this, let's say Mi, that is 30.8. Now 5CO2 is 6.6 by 30.8. That is 0.21. Similarly, Y of CO is 1.4 by 30.8. That is 0.045. Y of oxygen is 3.2 by 30.8. This is 0.104. Y nitrogen is 19.6 by 30.8. This is 0.636. If you sum all this, you should get 1.00. So, because we had all the mole fraction given, and we have calculated the mass fraction, and you should add it. Do you have any questions in this problem? In the next problem, a mixture that is 15% carbon dioxide, 5% carbon monoxide, 10% oxygen, 70%. Okay, I think this is the same question. Sorry. Okay, an insulated rigid tank is divided into two compartments by a partition. One compartment contains 2.5 kilomole of carbon dioxide at 27 degrees Celsius and 200 kilopascal, and the other compartment contains 7.5 kilomole of hydrogen gas at 40 degrees Celsius and 400 kilopascal. Now the partition is removed and the two gases are allowed to mix. Determine the mixture temperature and the mixture pressure after equilibrium has been established. Assume the constant specific heats at room temperature for both gases. So we have to calculate the equilibrium or the mixture temperature and the mixture pressure after at the end of the mixing. So for this we will be needing the volume of the total mixture. So we can start calculating the individual volumes. Say this is compartment 1 and compartment 2. Compartment 1 P1 V1 equal to N R P1. That is P1 is 200 kilopascal, 200 into 10 power 3. V1 is equal to number of moles is 2.5 into R is 8.314. To have it in joules, and into T1 is 27 degrees Celsius. This is 300 kilo. And Similarly for 40 degrees Celsius, it's 313 kilo. So this is 300. V1 is 2.5 into 8314 into 300 by 200 into 10 power 3. So we have the value of volume 1. This is 31.18 meter cube. Similarly, P2 V2 is equal to NR. So this is N1 into R into T2. So this is 400 into 10 power 3 volume 3 is equal to, this is 1.5 kilomole into 8314 into temperature is 313 Kelvin. So we can calculate the value of V3. 7.5 into 314 into 313 by 100 into 10 power 3. This is 48.8. Sorry, it is supposed to be V2. Now, volume of the mixture would be, after mixing, would be 31.18 plus 49.8. That is 79.98 meter cube. So we have the volume of the mixture. Now we have to equate the internal energy initial to final. Initial internal energy will be same as final internal energy because there is no heat transfer to the surrounding, and this is got by CV into temperature of CO2 plus CV of into mass. So UI is NCO2 CP also CV on molar basis into temperature of CO2 plus N hydrogen CV of hydrogen on molar basis into temperature of hydrogen. So here we do not know the molar basis constant one specifically, and we know gamma for CO2, since it is a triatomic gas, it is 1.33, and gamma for the hydrogen is 1.4 because it is a diatomic gas. So CV of CO2 can be written as on molar basis R bar by is 1. I think we derived this in the last session, last program. Yes. So here we have calculated. This is a and this is 0.333. So CV bar would be 14. It is 25 kilojoule per kilomole Kelvin. Similarly, CV of hydrogen is R bar by gamma of hydrogen minus 1, that is 8314 by 0.4, and that is 20.78 kilojoule per kilomole Kelvin. Now, to calculate the initial internal energy, we had NCO, or we write initial internal energy is internal energy of CO2 plus internal energy of hydrogen. So internal energy of CO2 is NCO2 CV of CO2 on molar basis into temperature of CO2, that is 2.5 kilomole into CV of CO2 is 25 kilojoule per kilomole Kelvin, and temperature is 300 Kelvin. That is 18750 kilojoule in total. And similarly, U of hydrogen equal to N of hydrogen CV of hydrogen into temperature of hydrogen. So this is 7.5 into this is 20.78 330. This is 48781 kilojoules. So UI is 18750 plus 48781. This is 67,831 kilojoules. This is the internal energy in the initial state, and in the final state this is given by N mix CV mix into T mix. Now CV mix can be given by summation of xi into CV mix CV of the integer component, and that is for xi we will have for the first component carbon dioxide of 2.5 kilomole plus 2.5 so 1.5 is 10 into 25 plus 7.5 by 10 into 20.7. So see shares 67,531. So Tmx is 67,531 divided by 10, 21,835. This is 67,531 divided by 10. This is 309.3 Kelvin. You can also see, you can take a molar average of the temperature and then to be the same. So for example, you can have 0.25 into 300 plus 0.75 to 330. So this is again 309.7. So we have calculated the temperature of the mixture. Now we have to calculate the pressure of the mixture. So P mix V mix equal to number of moles of the mixture into R of the mixture into T of the mixture. Here V of the mixture is V of CO2 plus V of hydrogen. That is, we have already calculated, that is 79.98. This is Q. Now R of mixture. Okay, anyway, on molar basis it is only the universal gas constant and there is no problem about it. So P mix is equal to R mixes is 2.5 plus 7.5, which will be 10 into 8314 into temperature of the mixture is 309.3 divided by volume, that is 79.98. This is 321,520 pascals. 321.5 kilopascal. This problem is clear. The next problem, a 0.9 meter cube rigid tank is divided into two equal compartments by a partition. So that means each compartment will have a volume of 0.45 meter cube. One compartment contains neon at 20 degrees Celsius and 100 kilopascal, and the other compartment contains argon at 50 degrees Celsius and 200 kilopascal. Now the partition is removed and the two gases are allowed to mix. Heat is lost to the surrounding air during this process. In the amount of 15 kilojoule. Determine the final mixture temperature and the final mixture pressure. So now both the constant volume specific heat will be the same on molar basis because both are monatomic gas. So for monatomic gas, gamma will be 1.667. So using this we can calculate the CV of the individual gases. So for example, CV of the monatomic gas like neon will be this will be R bar by gamma minus 1. So we have this is 8.314 divided by 0.667. So CV can be calculated. This is 12.46 kilojoule per Now we need to know the number of moles. So assuming neon is in the first container and argon is in the second container, V1 equal to N1 R bar T1. So here N1 is the unknown. We have V1 by R bar T1. Pressure is 100 kilopascal divided by 10.3 into volume is 0.45 divided by R bar is 8314 into T1 is 20 degrees Celsius, that is 293 Kelvin. This is 0.0125 moles. Similarly, M2 will be 200 into 10 power 3 into 0.45 divided by 314. So this will be in kilomoles, so you can write it as 18.5 moles. This is in moles. So neon will take 22.4 or 1. It doesn't matter much because in the end we are going calculating the temperature, and here we will have 50 degrees Celsius, that is 50 degrees Celsius. 323 Kelvin. So this is 323. This is 0.0335 moles. So we have 22.4 energy is internal energy of neon plus internal energy of argon. Internal energy of neon is R, right? Internal energy of 1 plus 2, and U1 is M1 CV1. CV1 and 2 are same, and then T1. Here M1 is 18.5 into CV is 12.46. So here I can write this also, right? 12.46 joule per mole Kelvin, and into temperature T1 is 293 Kelvin. So U1 can be calculated. That is 67,539 joules. Similarly, U2 is 33.5 into 12.46, because CV is same for both the monatomic gases, and temperature is 50 degrees Celsius, that is 323 Kelvin. This is 134,823 joules. So we can calculate the initial internal energy as U1 plus U2, that is 67,539 plus 134. This is 2,362 joules, and this is same as U final, and U final is given as M initial into CV is the same into T mixture. And they also said that some kilojoules of energy is lost, so that is 15 kilojoule of energy is lost. So that means U initial equal to U final plus Q, and that is so this is correct. So this is plus Q. Q is 15 kilojoules. UF is initial of 202,362 minus Q is 15 kilojoules, so it is 15,000, and so there's we'll have similarly N mix can also be calculated. This is 187,362 joules, and N mix is 18.5 and 33.5. So this is 18.5 plus 33.5. So this is equal to 52. Now, writing this again, we'll have 187,362 on left hand side, on the right hand side we'll have 52 into CV is 12.46 into T mix. So T mix is this is 289.17 Kelvin. Similarly, B mix can be calculated. So N is 52 into R bar is 8314 into temperature is 289.17 divided by B mix is 1. cylinder device contains a mixture of 0.5 kg hydrogen and 1.6 kg nitrogen at 100 kilopascal and 300 Kelvin. Heat is now transferred to a mixture of constant pressure until the volume is doubled. Assuming specific heat at average temperature, determine the heat transfer. So the initial pressure temperatures are given. T1 is 100 kilopascal. T1 is 300 Kelvin. V2 by V1 is 2, and mass of hydrogen is 0.5 kg. Mass of nitrogen is 1.6 kg. So in this process, we can assume a polytropic process where PV power n is equal to constant. Oh, sorry, it is given as a constant pressure process. So the work done is calculated by P delta U. And then heat transfer is delta U plus W, and here W is given by P del V. We have to calculate the internal energy change. Now R of hydrogen. So we can calculate the R of the mixture, like V of the mixture, that is V1 equal to V mix. For this we need to have P1 V1 equal to MR T1, and here R is R of the mixture and M is mass of the mixture. Now V1 P1 is known. So to calculate R of the mixture, we have R by molecular weight of the mixture. So calculate molecular weight of the mixture. We have 1 by this, 1 by molecular weight of the mixture is summation of mixture is 0.238 divided by molecular weight of hydrogen, that is 2 plus 0.762 divided by molecular weight of nitrogen, that is 38. So mx can be calculated. This is 6.84. Can be calculated, that is 8314 by 6.84. That is 1215.5 joule per kilogram Kelvin. V1 can be calculated. That is V1 is m of the mixture, r of the mixture, t of the mixture, that is t1 divided by p1. M of the mass of the mixture is 2.1 into 1215.5 into temperature at the state 1 is 300 Kelvin. Pressure 1, that is 100 kilopascal. This is 7.6 by 466. We know V2 is 2V1, that is 2 into 7.66. This is 15.32. So work done is C into delta V plus this. Pressure is 100 kilopascal. It is 100 into 10 power 3 to 15.32 minus 7.66. This is 766 000 joules. 766 joules. CV of the mixture divided by molecular weight of the mixture. We calculated the molecular weight of the mixture earlier, and CV mixes CV because both are diatomic gases, we can say it is universal gas constant by gamma minus 1, that is 8314 divided by 8.314 divided by gamma minus 1 is 0.4. That is 20.785 kilojoule per kilo mole. CV of the mixture on mass basis is 20.785 divided by the molecular weight of the mixture, that is 6.84. This is 3.1 change in temperature, that is 6